Hey everybody, it's Mr. Carr again. Today we're going to be looking at section 1.3. We're talking about continuity and behavior and limits. To start, we're going to actually focus on limits and what they are and what they're representing here. Okay, so a limit, if the value of f of x approaches a unique value, we'll call that L here. As x approaches c from each side, then the limit of f of x as x approaches c is L. Okay, so what that is referring to is this. If you have this as your function, right? You come from the left side to the right side, closer to this value C, this X value C, or your input, I should say. The limit exists as long as your graph is getting closer and closer and closer to this output value from here. It's also getting closer and closer from the other side. They are approaching the same value. So as long as they're going to the same value, then we say the limit exists. So it looks like this. Okay. So when I read this, it's the limit as x approaches C, the function is approaching L. Okay, the limit of f of x as x approaches C is L. That's a better way to say it. Okay, so let's take a look at what that kind of looks like for what's called continuity. Okay, continuity has to do with whether or not a function is continuous. So it is continuous at x equals C if it satisfies the following conditions. F of x is defined at C. That means that if you plug in the C value, it does come up with a real value and not some kind of impossibility. F of x approaches the same value from either side of C. Okay, so again, on the numbers that are lower than the C value and x values that are larger than the C value, they are coming towards the same value as for the function of what you got for f of C. Okay, the value that f of x approaches from of each side is that f of C. So it's not something where it's approaching, let's say f of x is approaching 2 from both sides. Okay, you're getting closer to 2, but then the actual value is 5. That doesn't work. There has to be, if f of c is 2, the numbers have to be approaching 2. Okay, so that's the steps that we're going to take to figure out if a limit exists and whether or not a function is continuous. So a continuous function is one that does, it's a solid curve. There's no holes, there's no breaks in the graph. That's the idea. All right, so these are our steps. We're going to evaluate at x equals c. Then we're going to figure out, is it approaching from both directions? As it approaches c from both directions, does it exist there? And is that value approaching f of c? Okay, so we look at this example here. So determine whether f of x equals 1 divided by 2x plus 1 is continuous at x equals 1/2. Okay, so the first thing we're going to do is we're going to evaluate f of 1/2. We're going to plug in that c value. So it looks like this: 1 divided by 2 times 1/2 plus 1 here. Okay, so f of 1/2 is going to be 1 over, so we got 2 times 1/2 is 1 plus 1. So f of 1/2 is going to come out as 1/2. So it exists. So step 1 is good. Step 2 is going to be determine if I go lower than 1/2, so 0 or 1/4 or 1/8, like are those numbers from the lower end getting close to 1/2 for the outputs? Same thing above it. If 1 or 0.75, if those numbers are getting us closer to 1/2, then that will also do it. So we're going to look at a table that already exists for us to help out with this. The best way to do this is to construct this table. Now, you can just kind of create this in your graphing calculator. You don't, but bottom line is, if you don't have any kind of graphing calculators, you're going to make your own table then. So again, this is my input. X is 1/2, 1/2 or 0.5. The output is also 1/2 or 0.5. Okay, so let's look at what happens. If we plug in the 0.49 for X, you should come out to a decimal number like this. If you do something a little bit closer to the 0.5, you put 0.499, you get even closer to 0.5 here. If you do 0.4999, that ends up getting you closer there. So these values are getting from here to here to here, they're getting closer to 1/2. Same thing when we go above that. So if I look at 0.51, that gives me 0.495. I get a little bit closer to 0.5, 0.50 by doing 0.501. That's even closer to 0.5. 0.5001, you round it off, it actually is 0.5. So again, we are approaching 1/2 from both directions. The low end is getting closer to 1/2, and the upper end is getting closer to 1/2. Okay, so that means since we have, so the question is, does this exist? Since we are getting closer to 1/2, which is what we evaluated, we know that it is continuous at that point. Okay, So we've got all of our conditions are met. It exists at 1/2. It's approaching the same value from both directions, and the value it's approaching is the output of 1/2. And here's a graph to show that. We can see why this is continuous here, because here it is approaching the same value here, and then it also exists at that point. Okay, well, let's talk about when it's not continuous. So that's a discontinuity. We have 3 types of discontinuity. We have an infinite discontinuity, and that is if you are approaching the value c from both directions, you're actually not approaching the same numbers. It's going away from each other. So what I mean by that is this: if c is my value, if I come from this direction, it's going down to a negative infinity. It's going like further and further away there. But as I move from this direction, it's going up to a positive infinity. So that's an infinite discontinuity. They're not approaching the same value. There is a jump discontinuity, which is at x equals c, the x approaches c from the left and the right exist, but they have 2 values. So what I mean by that is if I look at the function here going this way, it's approaching this y value down here as my output. But when I go here, it's not approaching the same value. It's approaching this way, and it's this y value that's up here. So it approaches 2 different output values from the 2 different directions, from left and right. Okay, so that's a jump discontinuity, which is a piecewise function, basically. The last one is a removable discontinuity, which is a hole in the graph. Okay, so it's continuous everywhere else except at that moment. So this is actually going to fail the step 1. It does, when you evaluate it, it will not, it doesn't exist there. The limit exists, but it does not actually, it's not a continuous function because that's a hole in the graph. So again, we are approaching the same value here and approaching the same value here, but because of the hole, the f of x, or like basically f of c, is undefined. Okay, so this diagram kind of shows that, but we're going to look at that a little bit more, both algebraically and graphically, when we look at this next example. So we want to first determine whether the function is continuous at x equals 2, just by using the continuity test. If it's discontinuous, identify the type of discontinuity as infinite, jump, or removable. Okay, so first thing I'm going to do is, just like before, by step 1 is I'm going to evaluate what is f of 2. Okay, so I plug that in here. We're going to have 2 minus 2 over 2 squared minus 4. So that's going to give me 2 minus 2 is 0. This is going to give me 4 minus 4. So f of 2 is going to be 0 divided by 0. Well, first thing is this: I cannot divide by 0. So that means this is undefined. So what we know for a fact is it is not continuous, flat out. It fails step 1. Now the question is, which one is it? Is it infinite, is it jump, or is it removable? Okay, there's 2 ways of doing this. You can do the chart idea, and if I just kind of get a rough idea of what's going on with this, I can go ahead and double check something. Okay, yeah, I'll pull up a graph in just a minute here. But one thing I can do is I can try, well, if I'm looking at x equals 2, a little bit below that would be like 1.5. So if I do x of 1 or f of 1.5, I jump to the other side, I can do f of 2.5. Just to give me a feel for this, because if it's like wildly different numbers, I know that that's going to be either a jump or infinite kind of discontinuity. If I plug that in, I have 1.5 minus 2 over 1.5 squared minus 4. Okay, that's going to give me a 0.5 over 1.5 squared. Sorry, 1 second here. Sorry about that. I just had to grab a calculator. So if I do 1.5 squared minus 4, that comes out to a negative 1.75. So f of 1.5 is actually going to come out. Sorry, yeah, that was a negative 0.5 in my numerator. My bad. Okay, so if I do that, that's going to come out to a 0.29. On the other end, I'm going to have 2.5 minus 2 over 2.5 squared minus 4. So here I'm going to have 0.5 over, it'll be 2.25 when I put that in my calculator. So divide those out and I get 0.2 repeated. So 0.29 and 0.2 repeated, that might work out. So the problem with this is I've got to do more values to make sure that they are converging in the same point. What's a little bit easier is if I just go to a graphing calculator. So I'm going to go ahead and pull that up right now. Okay, so here's my graphing calculator. You can see where this graph is. I'm going to actually make that a little bit easier to see there. Okay, it looks like it's a continuous function. Okay, remember, we're looking at x equals 2 here. So a couple things I can do. For one, I can go with this. I'm going to turn it into a table and take a look. And you look at that, -2 is undefined. Okay, so -2, oh, -2 and +2. I don't care about this value right here, is +2. Okay, so that's happening over here. So you can see on here, if I kind of click and drag on here, I'm getting closer to 2. You see how the graph is getting, the y values are getting closer to 0.2. Okay, 0.24. It's undefined right at that moment. So if I come from the other direction, okay, I come this way, I'm getting closer and closer and closer to the same value, that 0.2, and then boom, it's undefined. Okay, so that means we have, based on the graph and a little bit on here, we have a removable discontinuity. Okay, so again, if you're using the graph, you can identify it by the fact that you have a hole in the graph. You see that it's approaching the same number from both sides. It looks like a continuous graph, but it doesn't exist at that one moment. Okay, so it's not a broken up function, so it's not piecewise, and it's not infinite. Well, it means infinite at a different spot, but not at 2. Okay, so identify a point of discontinuity here. Determine whether this function continues at x equals 2, just by using the continuity test. So at x equals 2, so same thing as before, we're going to evaluate f of 2. Since this is a function here, since this is a piecewise function, we need to first identify which part we're going to put it into. X is greater than or equal to 2 here, so it goes into that. It'll be 2 plus 6. So f of 2 is equal to 8. Okay, so step 1 is done. It exists, so we know it. So we know that f of c is an actual output here, not like the last one, which ended up being a hole. So the next thing I want to do is I want to look from both directions. So I could do something like, what is f of 1.5 and f of 2.5? Compare those two values. See, they're going to be getting close to each other. So f of 1.5 is going to be 1.5 plus 6, which is going to give me 7.5. But 2.5, if I plug that in, that's going to be, oops, no, sorry, I did the wrong thing. My bad. Because 1.5 is less than 2, is going to go in the other one. Okay, so it's going to go into 1.5 squared minus 4. Okay, so when it does that, I'm going to get a negative 1.75. Okay, for f of 2.5, I'll plug that in, that's going to be 2.5 plus 6. F of 2.5 is equal to 8.5. This is a big difference. I think that what it sounds like to me is it's probably going to be a jump discontinuity here. It's not going to be removable. They're not getting close to the same number. Okay, and it's also not an infinite one because it does exist at that moment of x equals 2. But we're going to go ahead and pull up the graph here in just a second, just so we can compare. Okay, we're back with our graph, and you can see, yes, it is a jump discontinuity. Look here, this value, here's my 1.5, that here is getting closer to 0, like that. At 2, it is not going to be, it's not going to be defined at 2. We get really close, it just jumps off because I'm jumping up here to this function now. Okay, this function exists 2, 8, we saw that one, but it's a different value from what this one is from approaching on here. Okay, so we get a jump discontinuity at this point. All right. Last thing we're going to talk about today is with the intermediate value theorem. So if f of x is continuous function, okay, a is less than b, then that means there's a value n such that n is between f of a and f of b. Then there's a number c such that c is in between a and b, and f of c equals n. It's kind of goofy, a long thing, but here's what it's really getting at. The important idea is this. If you have a continuous function, you know you definitely have a 0 if you, for example, have at a and f of a, that's a negative value for the output. B and f of b puts you at a positive value. That means that you are somehow crossing the 0. The only way for that to work is if your crossing's there. So this kind of helps us determine the number of zeros. So let's look at an example of this. So approximate the zeros using our theorem here. Determine which consecutive integers the real zeros of this function are located on the interval -2 to 2. So all we're going to do is for each of these, we're going to plug in. We got f of -2. I'll plug in f of -1, f of 0, and then I'll do f of 1, f of 2. I'll see what kind of space I have. All right. So -2 squared minus, whoops, minus a -2 minus 1, -1 squared, space here, minus a -1 minus 1, f of 0, it's going to give me 0 squared minus 0 minus 1. And I think I'm just going to write those down and just do the rest real fast. Okay, so we got 4. This ends up being 4 plus 2 minus 1. That'll give me 5. This one here, f of -1, that's going to be 1 plus 1 minus 1 is going to get me 1. Okay, when I plug 0 in, I get a -1, so f of 0 is going to end up being a -1 here. If I plug in 1, that's going to give me 1 squared. I'm just going to do that in here. So I do that, that's going to be 1 squared is 1, minus 1 is 0, minus 1 is a -1. So I get -1 there. And for my last one, f of 2, that's going to be 2 squared is 4, 4 minus 2 is 2, 2 minus 1 is 1. Okay, so the question is, between which consecutive integers are there real zeros? Since I am moving from a positive output down to a negative output, we have to cross the x-axis somewhere here. That's the only way that's possible. So I have 1, 0 between -1 and 0, or I should say this, x equals -1 and x equals 0. Okay, and the same thing happens right here. Going from 1 to 2, we go from -1 up to a +1. So we're crossing again. So 1, 0 between x equals -1 and x equals 0, and between x equals 1 and x equals 2. Sorry, running out of space here. Okay, so that's what our goal is. We're trying to determine where does the 0 exist between integers. Okay, and that is it for today. So we'll continue a little bit more with some limits and end behaviors, but that's it for our first day of 1.3. All right, take care, everybody.